I'd like to thank the organizers for organizing what has already been a fabulous AGCT. I love how carefully the schedule gets carved up with so many talks and arrangement. It's been a great time. I'd like to tell you about reducing models for branch covers of the projective line, and this is joint work with Kieran Schembri and Sam Schiavone. Okay, now, I managed to reduce my talk to one meme. Okay, so here it is. Now you'll see the character on the left. Maybe we'll call him Grothendrake. And he is very unhappy with the equations on the top, but much happier with the equations on the bottom. All right, well, unfortunately, I have to tell you more details. I wish I could end there. I kind of went all in on the meme. But so where does this type of problem show up? Well, if you have a finite branched cover x to p1, when it's unramified of curves, when it's unramified away from 0, 1, and infinity, we call it a belly map. We already saw in the morning talk how the number of short orbits, when you look in characteristic P, has an outsized impact on the size of the automorphism group. And that's just a general principle that somehow all of mathematics is encoded in P1 minus 3 points in many ways of understanding that. So people do things like compute belly maps. This is like my visual way of thinking about branch covers. Implicitly, I'm thinking over characteristic 0 and things over number fields. That's what was so interesting about belly maps. Grothendieck said, well, they're just combinatorially described by where they're ramified, and yet we have an action of the absolute Galois group on them, so we really should try to understand it better. In fact, if you go into his esquisse, you'll see a comment to the effect of, I tried to compute a few of them by hand, and no pattern seemed to emerge from them. I just am tickled by the idea of the actual Grothendieck, not Grothendrake, computing equations by hand and finding it to be a complicated matter. Of course, these days, there's the LMFDB. Okay. And in the LMFDB, there is, once it loads, this is in the beta site. There's a database of belly maps. For some reason, we have 1,111 of them, which makes me reluctant to add any more. Okay, we'll just add 10,000 of them. Yeah, so great, great idea. I did not ask for audience participation yet. Okay, so in a method to compute these belly maps, you end up with equations that are very complicated. So I just clicked on random. And actually, this is a slightly better version of one that's already kind of bad. Okay, so I guess all you could see from this is when the number field is already pretty complicated, and that's the thing that Grothendieck was interested in, the equations for the curves can also be pretty fearsome. I'm feeling lucky. So here's another one where this is an expression for the equation, and here's an equation for the belly map. That one doesn't have quite such the same impact, but I feel like you see the belly map a little bit more this way. So the expression in the meme was also one where reducing the size of the equation had a more dramatic effect, but what we need is something systematic that'll run over all 1,000 and change maps. They work over number fields too, which might have integer class numbers and so on, and so we need to be reasonably efficient. So, and you guys know what this feels like. You do a calculation, the way that we do it is power series expansions on something, and you get an object which is correct but very large because of the choice of coordinate. And in order for any kind of computational algebraic geometry, coding theory, cryptography to happen, you need to reduce the sizes of your expression. So that's the general problem. Okay, so maybe if we step out a little bit more broadly, given a model, so some kind of equations for a map of schemes over a number field, the problem would be to find a reduced model with smaller size. Okay, so that's not well defined yet, but I guess you could count the number of characters required to write the output and say I want to write fewer characters. So at least we can be precise that way. There's another thing which is related, which is called minimization, where you seek to minimize an invariant, like the absolute discriminant. So you decide you want to represent things by a Weierstrass model for an elliptic curve, or y squared equals f of x, and then you try to, within those fixed changes of coordinates, find one that minimizes the absolute value of a discriminant or some other invariant, okay? And these words are sometimes used interchangeably, and sometimes they go together, and I'm not going to try to split hairs about what they mean. Very often, a successful algorithm for one has an approach for the other. And maybe it goes without saying that these are hard problems in general. I mean, not just hard because I phrased them vaguely, but how do you know which coordinate change to make? You might want to divide this coordinate by 2, but it makes it worse in another way. So we really, but because of their utility, we're in the mode right now, maybe less to have a deterministic polynomial time algorithm, rather you just want to be able to press a button in your favorite computer algebra system, whatever that may be, and get a smaller equation. Okay. Here are a couple of such situations. There's elliptic curves, Tate's algorithm for minimal Weierstrass model. Mikkel Stoll has something like point clusters. So if you take a finite set of points in a projective space, if you want to think about binary forms, or equivalently y squared or y to the n equals that binary form, that's work of Stoll-Cremona and Hudson-Stoll. There's n covers elliptic curves. That sort of shows up naturally when you do n descent on an elliptic curve, and there's reduction theory there. There's also an unpublished work of Van Hoy and Novason from 2005 that suggests a method for curves at least over Q, which has some interesting ideas, basically trying to bootstrap off of the idea that Paul Red-Abs works pretty well for number fields. You take the ring of integers, you find a short vector in that ring of integers, and you try to think about the curve over Q as parameterizing number fields. So that is available. And most recent work, in case you get into this thing, is a really nice paper by Elson, Hans, and Stoll, where they work with hypersurfaces in projective space, looking at possible weights to put on invariants. It's really quite general and implemented in Magma. Okay, so we're going to today talk about reducing, minimizing, not just abstract varieties in projective space, but really thinking about the model of the map. Okay, so it's really the Belly map that we care about, and that's a slightly different problem than these other ones where the curve is represented in a particular way. So that's what's new. All right, and any good algorithm should have input and output, I think. So the input is a map of curves. You can take that to be the Belly map, but it will work all the same. And the output will be some kind of smaller model. And our steps are as follows. First, we found the smallest way to write curves down is with a possibly singular plane model. That shows you where we made a choice, but trying to reduce bits, we're not trying to make a smooth model of high codimension in projective space. And then with that plane model, we're only going to do rescaling of the coefficients of the plane model, and I'll show you how to do that, which really does find, in some sense, a real minimum. And because there might be several small plane models, we do this a couple of times and then take the smallest ones, whatever that means. Okay, sorry, that went by a little bit fast. That's the overview. Okay, so 2 steps. First, find plane models. Second, I'll show you how to reduce the coefficients. Okay, so how do you make a plane model? Well, the map phi describes a function field extension. So T will be the coordinate on the P1. K is the number field over which it's defined. So what we're looking for is another generator of the function field. So some small function x, such that the function field of big X is ktx. So if you had such a choice of coordinates t and x and any other way of representing the function field, there is a single plane equation ftx. They're algebraically dependent. And you can take the map to just be the projection onto the t coordinate. So I told you I wanted small equations, and I promised you can't beat that for a small equation, for a map. Okay, just take the t coordinate. We aren't going to have to pay the penalty, you will see, by considering the equation a certain way. Even Groth and Drake found a very small equation this way. And if you do this, it's just elimination theory to write down the plane equation, and that also has an efficient implementation. Okay, so now I hope I've convinced you what I need is one other small function on the curve, which is enough to generate the function field. And you might have small functions coming from all kinds of places. So maybe they came as the input, maybe you had a modular curve or a Shimura curve and some other reason why you know that this coordinate is going to be useful. Sometimes you have gonal maps, if you know that your curve is small genus. If it's hyperelliptic, you may want to use that as the other coordinate. This actually makes sense to think over finite fields as well. If we have a small model in characteristic 0, then when we reduce mod p, it will also be a small model. So there's no harm in investigating what is possible over the curve. For those of you that are thinking right or like to think in characteristic p, this is already a problem that you might try to find, to consider in this situation. So let me tell you how we find all of those are allowed. Here's what we did to find a small function. The idea is, if the map is small, then its ramification points should be small. And there's nothing smaller than 0 and infinity. I was expecting to get more laughs from that. Okay. It's actually because I can tell because you're mathematicians and not humans. So you're like, oh yeah, infinity is just a 0 of the denominator. So good job. Okay, that's what I meant. And that's like an idea, not a theorem. It's just like, that's what we found by trying really hard to make small things. Okay, so what does that mean? That means I should look for a function x which is supported at the ramification points as much as I can. So here's how I would write that down. If I look in the divisor group, not of k, there's always one typo, isn't there? So that should be an x. So you take it's so close to an x, no wonder. So you take the divisor group of x, and you look at the subgroup of k rational divisors supported on the set of ramification points, okay? So I don't want to make a field extension. I do need to, if we're going to satisfy Grothendieck, we have to keep the field being over k, but I can take sums of points, Galois stable divisors, okay? So that gives me some infinite thing. And then for each d, I can ask for those of degree d. Degree of the divisor is degree of the 0 part, or the equivalently the degree of the, let's say the max of the degree of the plus part and the minus part. And then here's where we did something that you might not have done, but it seemed to work really well for us. We look for divisors with the property that in the L space of that divisor, there's exactly one function. Okay, now this is a very different type of reduction theory if you have like the x coordinate is only well defined up to ax plus b. Now you have to work sort of additively within that vector space. I would say something like, oh, your space is two-dimensional. Well, require it to have a 0 at one of the ramification points, and now it's one-dimensional. So that's sort of how we are forcing the connection of the coordinate with the structure of the map phi. Okay? And the good thing about this is that we end up with functions that are unique up to rescaling, just by k cross. Okay? So, and we have enough source of them. So maybe another way you could view this is if you had a map of a modular curve to P1, maybe you also want to throw in not just the j equals 0 and infinity and 1728, but you might want to throw in the CM points too, because those might also, you can just chuck them in the same way. So a curve with points, I'm using ramification points here, but that also seems to, if the coordinates of those should be small, then the map should also be small relative to them. Okay? Now we have some possibilities for small functions x. They're well defined up to rescaling, so let's figure out how to rescale them. So here I'm going to work a little bit more generally because actually the notation's a little bit better. So you have some polynomial, it's got coefficients a sub nu. I use multi-index notation, so the exponent is also called nu. And what would rescaling look like of this polynomial f? Well, I could rescale the x variables, and I can rescale the whole equation. So that gives me, if it's n coordinates, then I have n plus 1 parameters for rescaling. We're focused on the curves case, so I have three things to rescale. And you want to find something that when you rescale, we decided that it was smallest if you took integer coordinates. That's also a choice. Sometimes the smallest one is where you just allow a couple of 1/2. So I don't know that this is always truly the minimal thing, but it seems popular, enough of a choice. You may also want to do something like, if you choose a power basis for your ring of integers, you may actually want to require that it be integral with respect to that power basis, inside the order. So there are choices there. But anyway, our idea is work locally, and just for every place v, you minimize the valuation by saying, okay, I got to plug in pi, my uniformizer, and I want to try to minimize the total valuation of all my coefficients. So let me show you what that looks like. Okay, so we'll do the non-Archimedean case first. So remember, we had our coefficient f, and this is what it looks like when you substitute in for b and c. You like evaluate with the b's and then rescale by c. Okay, so I want to minimize the sum of the values, the absolute values, thinking of the higher the valuation, the larger the coefficient. Okay, so we want to minimize the sum of the ORD p's of all those coefficients. And I insisted that they be integral. All the coefficients being integral. Okay, so what type of problem is that? Do you guys recognize? What does that look like if you expand it out a little bit? Well, if you wrote these coefficients, remember I'm trying to modify it by a power of the uniformizer. So I write my uniformizer to some zi. That's what my b is supposed to represent, and the same with the c. Then when I plug into the ORD, now instead of looking exponential, it looks additive, right? So when I substitute in the p, then it's p to the nu, but that's, so it's sum of the nu times z, and the ORD acting like log. So I want to minimize that linear function. The nu's are fixed. The z and the w are the things I'm trying to solve for. And then there's some linear inequalities on the coefficients which insist that it is integral. Okay, and with dramatic applause, this is an integer linear program, and those can be solved efficiently. Okay. Should I have called for applause for the meme? That really was the point of the talk. Okay, all right. So here's an example when p is equal to 2 and some equation that obviously has some problems at 2. Okay, so you substitute in, I got, well, how many of those? 6 coefficients. I write down the exponent vectors. I look at the ORD2, and we want to minimize the sum of those coefficients. And here was my attempt to draw the picture of the integer linear program. Just to break up the equations. For each one, I get a greater than or equal to 0, and then this was my attempt to show you what happens with an integer linear program. You take your positive Orthon of some kind, and you have this single thing you're trying to minimize, and boop, the first moment it hits, that's your minimum. Okay, and it's a really well-studied problem, super fast, and available in your favorite computer algebra system. Okay, and this minimum occurs at some integer point. You translate back that to the coefficients, and look at how nice that is. So maybe you can take that away, even if you don't have a belly map and you just need this kind of thing. I hope you'll remember this is like an integer linear program type of problem to solve. Okay, and there are class number issues. But the idea here, the thing to remember is even if you have class number bigger than 1, principal elements lie in a finite index sublattice. Okay, so p might not be principal, but some power of p is. So if you kind of do them all at once, then you're going to have to require that this thing you're transforming by is principal, but that's just going to be index h sublattice in the coefficients that you're working in. Now, I wrote this out in terms of, oh, geez, okay. I don't know that. This is like you saw the slide, so now it's been established. Okay, but we're just going to go on. I hope the idea is enough to remember. Okay, and in the Archimedean case, you can do a similar thing, except it's not strictly by valuations, but you replace those with absolute values. You do have units around. That's really something different than if you're just minimizing curves over Q. So for the Archimedean places, now instead of the norm being like the valuation or something, you embed your units into using the log Minkowski embedding into R to the m. M is the real places plus complex places. For small, we decided to take the L2 norm, sum of squares. That's a reasonable measure of size. You could replace it with other norms. That would be okay. You'll see how L2 is really useful to us. And our action is now, because we've decided the valuations are all fixed. Now we only have the action of units left. Okay, so we have to transform our coefficients by units. And what happens when you take your fixed coefficient A and you multiply it by a unit in the log Minkowski embedding, all you're doing is translating along the hyperplane. So wherever that unit is inside the ambient real space, you're moving in some integer points in a hyperplane described by the trace equals 0. And there's a little fun exercise which you could do using Lagrange multipliers, I think, where the minimum on this plane is where all of them are equal. That's the usual thing that has to happen when you minimize a function and you know that it's kind of concave. So there, all of the coefficients are equal. So if you had judged one coefficient and you wanted to minimize it, the thing to do is move it as close as you can to like the barycenter, or whatever you call that. So in general, what you would like to do is to do that with something like the geometric median or something, where you have more than one coefficient. So you try to simultaneously minimize them. What does it mean to minimize this coefficient? Well, you want to get as close as you can to this median. So this expression here, this is the something fixed by the coefficient. This is your variable, and I want to minimize the distance. Okay, so if I sum all of those, I get an expression that looks like this. All right, and then you have to do the same kind of trick where lambda was a log embedding, so what looks exponential now becomes additive. And maybe this is kind of already intuitively clear, but I'm trying to minimize the distances, sum of distances, to a fixed set of points. The norm is given by a quadratic form. So this is like sometimes called a semi-definite integer quadratic program. I don't know that the terminology is completely clear on that, but let me show you there's a quadratic form that we're going to minimize, and we have integer solutions to it. That's what this should look like to you. And so if you expand it out, I decided not to show you even more ugly coefficients. You'll just have to carry with this that the absolute value is the sum of squares, and then expand out using the parallelogram law. I hope that's kind of clear. There's some function, quadratic function q, and that can be represented as a positive semi-definite thing. Sometimes you could lie on a line, so there's more than one solution. One of those eigenvalues might be 0, but other than that, it is positive definite. And then some scalar from not just the quadratic terms, but the linear terms. All right, and this is also a lovely standard problem. I won't ask for applause for this because it's real analysis, not number theory. But you write your symmetric matrix in a Cholesky decomposition, and you could do this in your linear algebra class. Okay, let me show you what it looks like in an example. Here's a polynomial with a root 2 in it. That coefficient looks kind of big, don't it? Nah, actually it's just a power of the unit. This happens all the time if you work even with elliptic curves over real quadratic fields and you compute the minimal model. It's not smallest because it didn't take out the units. Okay, so what are we going to do? Well, we're going to rescale each of the coefficients by a power of this unit. Okay, so you plug in and you say, with sum of squares with respect to these coordinates z1, z2, z3, here's what that looks like. This is not a dot product. It's really the sum of those coefficients because you're really moving inside that R2. And that, up to a constant, which when you're trying to minimize something doesn't matter. I pulled that out. That's the dot equals. This is the quadratic function that you need to minimize, where the zi's are integers. Okay, and the method to do that is really nice. Here's where you write it as a matrix, like I wrote out before. Looks pretty harmless, right? It's the type of thing you can plug in. And in this particular case, because I wanted to illustrate ideas and not have too many real numbers, the minimum is actually at an integer solution. If it wasn't, you would take the minimal real solution and then do a closest vector problem to find it. And after you do this, you reduce it, and there goes the thing that I sneaked in with the epsilons. Okay? So there you go. I would like to show you a demo in 1 minute. This is before the conclusion. Okay, so here's an example where I have a root r. This polynomial is x cubed minus 2, just to show you something non-trivial. I make P1 is my curve, just to make this example simple. That shows up often enough in our Belly maps. You make the function field, and there is the kind of thing that our Belly map algorithm produces as output. Nothing you want to show to anybody, okay? And so then I set verbose so you can see what's happening. And here I'll show you all reduced models of our function. So it goes through and they're zippity-doo-dah. All right, so I'll show you a little bit of the output here. It's trying with effort 9 to confine degree 1 functions because it's P1. It only took 0.9 seconds to look at a whole bunch of functions of degree 1 supported at the ramification points. And then it does for each one of those, it finds many of them, it does a p-adic and a unit reduction. Okay, and then it finds 10 such equations is what we do by default. So the top one we might consider to be the best. These 3 coefficients are the rescaling coefficients. So it's really kind of counterintuitive that, this one, the size of the coefficients doesn't always correspond to how the size of the equation is going to come out, but that's just because of the way of representing it. Okay, and I don't know, maybe some of these you would prefer to other ones, but they look pretty good. So there really might be a menu of options rather than just a best one. Okay, so the conclusion, I just tried to describe for you an algorithm that reduces a branch cover of the projective line. What's the basic idea? We find a small plane model, possibly singular, by looking for functions supported at the ramification divisor because we think that 0, infinity are small. The map is small, then the points should be small, and that's the extra data that I might not have in general if I just have a naked curve. And then I rescale the equation using a torus action. So I refuse to think about more complicated groups like AX plus B or GL2 or GLN. I only want to reduce with respect to K cross. And with all 10,000 plus Belly maps in the LMFDB, we very often see quite dramatic reduction, things that suddenly you do want to show to people. And if you think about those as parameterizing number fields, then this is also really helpful because now your equation is small, so when you plug in T, you also get nice small representatives. And if we had a next step, it would be to write the coefficients in the number field. That one that I showed you where it was really, really bad randomly, I think most of that is caused by writing the coefficients in a power basis for the ring of integers. That's obviously the wrong thing to do. You should use an LLL basis of the ring of integers, and then I believe even those will look nicer. And if it's useful to you, this torque reduction works in principle for any variety. Thank you very much for your attention.
Thank you for a great kickoff of the afternoon session. There are a lot of questions. Niels, wait until I...
Can you comment a little bit on the effect of choosing your low degree x coordinate and what kind of functions did you end up finding and how dramatic was the effect of that compared to having to improve your default coordinate choices?
It's a great question. I think they both had an important role. So, if we were to look at the examples that came out, in each step you will reduce it with a significant way. So I hope that's what you're asking for. Yeah, you would think that, oh, maybe one of these would be enough. But in fact, it's somehow, you don't really want to do the rescaling until you have one-dimensional space. And then once you have the one-dimensional space, I don't know which one to take in the line that's going to be smallest. And so they kind of go together. Yeah.
In particular, how good were the improvements that you saw in the degree of that other coordinate? Did you end up with lousy choices the first time around, or?
Yeah, it is not clear that, for example, sometimes we were surprised, and the extra function that we took was larger degree, but we ended up with a smaller equation. And I don't have a good explanation for that. I would like to think that if the top curve is P1, the right coordinate to use would be a uniform, a map of degree, function of degree 1, but that's not always the case for whatever reason. So I think there are some mysteries in your penetrating question, but as far as we can tell, we just compute the top 10 and pick one by the smallest one, because I don't think each curve, I think, is trying to tell us a story, so we have to listen.
Okay, another question. Elisa.
So you consider these belly maps, and if I understood, you really like belly maps, so I mean, this is enough for me. But could you do it, the algorithm can be adapted for more ramification points?
Absolutely. Nothing changes. I have no further other than yes.
Okay, yeah, but it's what I thought, Yeah.
Yes. And I think what that means, I'm not sure we're going to have a whole lot to say if you did y squared equals f of x and you took the x map. I'm not sure we will find anything new that way. But for more complicated maps to P1, if you're convinced that that map is supposed to be part of the data somehow, it's really not just the curve, but that map is interesting, then finding another small coordinate and minimizing with respect to that data, I do believe. There's nowhere do we need to restrict to 3 points.
Okay, one small question from me. So you use this p-adic type of optimization. So it means the system chooses what primes of the number field you deal with, it takes into account. So how do you bound this?
Yes, that's right. Well, we only reduce with respect to, when I start with my coefficients, I just say what are the support in primes of those coefficients. Because if I'm going to rescale them, I don't want to include suddenly new primes that weren't there before. So that's the basic answer. If the class number is kind of weird and large and there aren't enough primes coming out of that calculation, then sometimes it is advantageous to throw in a prime above 2 or some other small primes to help handle the large index of the lattice inside the larger one. Then you might, in order for something to be principal, it has to pay a cost. So you try to minimize that cost by focusing it on a small prime. But that's it.
Well, I guess it's time to thank you again.